Okay, hello everybody. This is Faith Tarek from Uponor. I'll be your moderator today. And the webinar we're doing today is called Inspect and Detect, a Guide for the Evaluation of HDPE Penstocks, specifically for run-of-river. So today's presenters are all from Uponor. We have Grant Thornley, Jerry Groen, and Daryl Sollenbach. So starting us off will be Grant Thornley, who is the Sales Director at Uponor Infra in North America. Grant has 25 years of experience in the industrial, municipal, and power markets. His expertise lies in pipeline infrastructure rehabilitation, asset management, storm and wastewater management, water transmission, and condition assessment. Next, we'll have Jerry doing a case study, going into a case study. He's our senior engineer. He's responsible for overseeing all of Uponor's design work in North America. He is a licensed professional engineer with over 40 years of design and manufacturing experience. And then finally, closing off, will be Daryl Sollenbach, who is our sales manager for Hydro. He takes care of the BC and Alberta region. Daryl has an environmental engineering degree and an MBA from University of Alberta. He's been with us for 15 years and responsible for Weholite engineering specification and promotions into the wastewater, CSO, SSO, conveyance, and stormwater markets. Daryl has 30 years of experience working with engineers and end users on construction and design solutions. So the topics of discussion for this webinar will be inspection of penstocks, differences in penstock materials, reasons for maintenance and activities, types of inspection equipment, and a case study inspection of BC Hydro Aberfeldie penstock, and then we'll finally look into some currently existing installed HDPE penstocks. So with that being said, we'd like to do a poll question in front of you on your screen. There should be a question popping up, so if you can answer, and then we'll go into some results right after that. So we'll give you about 10-15 seconds to go ahead and select your answer. So the question is, what is the most common penstock material that you currently work with? Is it concrete, steel, or structural HDPE? Okay, I hope everyone's got a chance to put in their answer, so we'll go into the results now. Okay, so 52.6% of you are currently using steel as per the poll. Concrete is number 2 at 26.3% of us, and then structural HDPE at 21%. So with that being said, I'm going to hand it over to Grant Thornley, who is our sales director, to begin this webinar.
All right, well, thank you very much, Faith. I appreciate that, and thank you for everyone online that's attending this. We hope that it's going to be very informative, and as always, at the end, if you did have any follow-up questions, we'll try to answer them as many questions as possible, but if not, you can always contact us directly. So just quickly, I'll step on our promotional soapbox just for a second. I don't want to belabor this, but if you're not familiar who Uponor is, Uponor has been manufacturing HDPE or high-density polyethylene pipe for over 50 years. We were the first company to actually innovate and manufacture large-diameter HDPE piping using our Weholite methodology. And when I say large, we're talking up to 11 foot or 132 inches in diameter. So very large piping diameters. We also make solid wall, and from our Weholite technology, structural HDPE panels or Weholite modular. Different aspects that we make. We talked about we make HDPE penstocks, but also we also do log debris jams. We also do surge tanks and so on. So different components of HDPE used in association with run-of-river. So getting into the meat of the presentation, so why inspect a penstock? Well, as you're aware, a lot of hydro projects were installed way back. I'm going to say some of them are actually in operation for over 100 years. So with any material, there's always a concern is that, well, what is the asset integrity of the particular materials that I'm running? And with penstocks, as you're aware, that if there is a failure within a penstock, it could be anywhere from a small leak to it could be more catastrophic, which is very large volumes of water washing out areas or potentially property damage, or worst case scenario, human life. So the purpose, very important to inspect penstocks. The inspection programs, like any asset management program, there is an asset management program for penstocks, typically regulated or guidelines being put forward by FERC, Bureau of Reclamation, or other, let's say, state or provincial legislation. And essentially it talks about how to efficiently operate and maintain that asset. The type of inspections employed typically takes the form of non-destructive, but you can have destructive in some scenarios where you cut out a coupon section, but the majority of the times it's non-destructive equipment that's being used. The inspection frequency for a penstock, this is a guideline. This could be from FERC or the Bureau of Reclamation, but typically you're looking at 1 to 5 years. One being, typically on an annual basis, you should be walking the line, doing a visual inspection, and then later on, from 2 to 5 years, you should be doing more of an integral inspection that could employ equipment. So that is doing typically wall thickness measurements within steel pipe, and it could be if you're using pre-stressed concrete cylinder pipe, which is PCCP, the acronym. You may want to be measuring to see if there's any broken wires or pre-stressed wires within the concrete pipe. If you have wire breakage, as you're aware, that you can lose integrity. If I have wall thinning up to a certain percentage, I could have a rupture within the pipe. So again, visual inspection at the very early stages of the program, and then later on more in-depth investigation. So the inspection of a penstock, what is the maintenance program? What does that entail? As we said, there's 3 basic categories for a penstock inspection. The main one you're probably familiar with is the visual inspection. The information gathered during a visual inspection is used to plan when we see any deficiencies or defects. We're going to be using that information that's gathered to really tailor and create a more in-depth inspection plan. But part of the things we're looking at when we're doing the visual inspection is, number one, the alignment of the pipes. Has there been shifts? If it's above ground and it's sitting on concrete girders, do I have movements in that? Particularly if there's soil movements in the soil, or it could be within seismic zones, that's very important. Other aspects, if it's a large diameter pipe, is it out of roundness? Is it now oval rather than being completely round? If you're using concrete or steel, many of them have linings. So part of that is that, do I have perforations or loss of linings in that particular case? And last, corrosion, erosion, or cavitation, which is the main. I'm going to say erosion. Typically, as you're aware, in penstocks, the 2 areas that we're really concerned with is at the inlet, just at the pondage area, where I have a transition or a bend, where I have high turbulences. That's typically where we see a lot of the wear or erosion or thinning. And also at the bottom of the penstock, when I have another transition or another elbow, which again kicks up a higher turbulence. Those are the 2 main areas that we're typically concerned with, but also I can have corrosion and erosion along the pipe as well. So different types of penstocks material. I won't belabor this, as I'm sure as your engineers or very familiar with the types of materials. But we typically steel riveted. I'm going to say a lot of these installed over 50 years ago, or even 100 years, when steel was inexpensive, and metalworking was the labor component for that was very inexpensive. A lot of steel riveted penstocks. Later on, we also saw wood stave. Wood, a very local and inexpensive material, a little bit more labor intensive to do this, but there's still a lot of wood staves in Runner River. That being said, as wood staves are slowly being replaced by other materials such as HDPE. Concrete, pre-stressed or PCCP, pre-stressed concrete cylinder pipe, that is also being installed as a very common material. Composite is kind of a new entry, or FRP, which is fiber reinforced polymer. Could be glass or carbon fiber, typically glass, embedded in epoxy. Good life expectancy and design life on those. And the last one is structural HDPE, which we'll be talking a little bit more in depth. So different types of materials, and of course with different types of materials, that employs or requires different types of inspection philosophies or procedures. And why is that? Well, material failure mechanisms, as you're aware, if it's steel, because of oxidation or redox reactions, I have steel and corrosion. It could be on the surface, on the exterior, or interior. Other things on visual inspections, buckling, if for some reason, maybe if I'm doing my fill and my vacuum or air release valves misoperate, or I pull a vacuum for some reason, I can actually get buckling of the metal itself. An incredible amount of power that can happen in buckling. This is a 1/4-inch steel plate, and it looks like it's folded over aluminum. Wood delignification. Typically, just as you're probably aware, if a pipe is filled with water and operating, the actual water, when it's completely saturated, acts as a type of, I'm going to say, an antimicrobial growth mechanism. But what you find is that if the wood, on the down seasons for Runner River, when the pipe is no longer full, you can get drying of the wood, and that's when you start getting the corrosion or rotting of the wood, and you can't see it really well, but in this particular picture, but you can see a lot of water that's spraying out through the sides, and that's very common from wood. Pre-stressed PCC pipe, you can kind of see a picture here, is the pre-stressed wires that actually keep the concrete in compression, have snapped, and that's through corrosion as well, abrasion or cavitation, as we talked about the inlets or the outlets of the Penstock pipes. We see a lot of abrasion or some areas cavitation. A lot of the abrasion is coming from sand and silt that's being abraded against the surface. And for FRP or sometimes repaired pipes, you can have delamination of the actual fiber or FRP cloth. So types of failure mechanisms. That's why it's so important to continually to walk the pipe on an annual basis and inspect to see if you're seeing any of the preliminary signs of corrosion or breaking the pre-stressed wires. As example, you'd have cracking along the longitudinal or see fissures along the sides. Buckling is a visual, and so on. So very important, again, always do your visual inspections on an annual basis. So the type of inspections, the most common pipe, as we saw from the poll, was metallic piping, and that could be steel or steel riveted. And regardless of whether you're using RFT, which is remote field technology, or magnetic flux leakage, or it could even be RFTC, which is remote field transformation coupling, they all rely on the same technology platform, which is magnetism. And as you can see within the diagram here, is what we're doing is we have an exciter coil and a receiver. And essentially what we're doing is we're sending a magnetic field through the wall from the inside to outside diameter of the metallic pipe. And as we pass that magnetic field through, we're measuring any deviations or fluctuations within the magnetic flux lines. And if we have a solid pipe, in this particular case, where as this instrument moves along the pipe, being typically pushed because these are large diameters, as it moves along, we see that because the wall thickness is the same, the magnetic flux or magnetic field doesn't change. But when we encounter pits or loss of metal, what happens is that the magnetic field changes. And it's the changes or the deviations in the magnetic field which is correlated back to the wall thickness of the pipe. So without getting into the in-depth of it, but that is essentially what you're looking for, is changes in magnetic flux. The key to this type of technology is for metal wall thickness or localized pitting, is you need to have these sensors, and you can see in this particular diagram, the sensors need to be in very close proximity to the surface wall. If it's too far away, it becomes very difficult to measure the magnetic flux. And I want to have as many sensors as possible to measure the complete circumference of the wall on the inside. And last, you can kind of see the tool down in the lower left is that you can see all the sensors, very large piece of equipment that you need to push through the pipe or pull through the pipe. It's incredible technology. It really gives you a very, very fine resolution and allows you to really assess the condition of the pipe, and from that assume whether it's in critical repair or whether you can do long-term repair, or maybe the pipe's even very good shape. But that is the type of technology we use for metal wall thickness, and it's the same technologies used for measuring whether there's any breakage in the pre-stressed concrete cylinder pipe, the metal wires. If there's breaks in the metal wires, then what happens? We have changes in the magnetic field flux. So that's just a quick overview and a very minor dissertation on how magnetic wall or magnetic flux leakage works. So from that, just to touch on, why would you use HDPE for structural HDPE? Well, as we talked about the failures and mechanisms, whereas corrosion, abrasion, and so on, is HDPE, because it's a non-metallic pipe, it does not corrode. So therefore, there is no metallic or magnetic flux sensing required. So that's a significant cost savings. Also, the HDPE pipe is chemical and pH resistant, so very high or very low pHs and every pH in between, it will not affect the pipe. And it's chemical resistant, so again, any oxygen or any other contaminants you can throw at it, it's an inert material. So very, very high structural integrity, as well as the inertness of the material, really allows you to get away from conventional inspection using, we're going to see very expensive tools, and really coming down to measuring, really the condition assessment is done by visual and not employing any expensive tools. So that is just a quick overview of the different materials used and the type of inspection tools used for metallic or PCC piping. With that, I'll now hand this over to Jerry Gronin, our senior engineer at Uponor, who will work with you and present on a case study of an inspection, field inspection of HDPE. Jerry?
Good afternoon. I wanted to talk about the Aberfeldie power station. Before I begin and talk about that specific station, I wanted to comment briefly about most of these hydropower applications are actually run-of-the-river projects. And essentially, they're hydro stations where there's no upstream storage of the water. Run-of-the-river means that a portion of the river flow is diverted to create power, and the water is immediately returned to the river after it goes through the turbines at the power stations. So typically, we're borrowing the water from the river for a period of 10 to 15 minutes. Aberfeldie, however, is a more traditional hydropower station with upstream storage, the dam on the Bull River in central BC. The original station was built in 1922. It was rebuilt in 1953 and then rebuilt again starting in 2007 and completed in 2008. station itself is located about 35 kilometers east of Cranbrook, and it produces, after the redevelopment, about 25 megawatts of power. It has 3 turbines in the powerhouse. And the reconstruction involved increasing the flow and the head, and that was essentially achieved by moving the powerhouse downstream from the previous powerhouse, which was right at the dam. We moved it down about 3 kilometers. And most of that distance was about, 2,700 feet of 132-inch low-pressure pipeline, Weholite pipeline. I'm going to just flip back for one moment. It indicated that there's increased flow. Flow testing has been previously conducted on Weholite in rigorously controlled environments, only in relatively modest sizes. So that's 15-inch, 18-inch, and the metric equivalent of 30-inch. Testing was done to determine the Manning's N, the Chesney C value, and the absolute roughness of the pipe in those sizes, and then had been scaled up for larger pipes. What we see with the, as there's an increase in size, there's a slight reduction in loss per unit length of the pipe as the size increases. And that's really because the width of the profile that's used to make the pipe gets wider and wider. So we get slightly lower Manning's N and Chesney C factors as the pipe size increased, but the absolute roughness is fairly consistent regardless of size. And for very large pipe used in hydropower stations, the absolute roughness is the value that's typically used in the hydraulic calculations that are done for the project. The project was relocating the penstock, the steep portion of the penstock leading to the turbines downstream, and of course accumulating additional head as we did so. So there's a fairly consistent internal pressure, which is based on the difference between the hydraulic grade line and the elevation of the pipe, and it's about 20 psi for the entire project length. So Weholite polyethylene profile wall pipe is considerably lower in cost than a steel pipe. So designers typically want to maximize its use before the transition to steel occurs. And it's possible to do that, to accumulate as much head as you can by running the pipe at a fairly flat elevation. And that's really because of the limitations in pressure that are available with polyethylene pipe. Obviously, with steel materials, you can go to much higher pressures. So a steel pipeline would be typically run at much closer to the river. With polyethylene pipe, we're trying to run the pipe as flat as we can for as long as we can in order to maximize its use because of its lower cost. One of the experiences has been, however, that where we change from polyethylene to steel, typically some of the waters have been quite corrosive to the steel, and this is particularly so at the joints where the welding occurs. When we talk about joining on the Weholite, the use of the term like welding is a bit of a misnomer, because normally in welding there's a change of state from solid to liquid and then back to solid again. And in steel welding, the various elements in the steel alloy convert back from liquid to solid at different temperatures as the joint cools. And that's, of course, the heat affected zone. And it's in the heat affected zone where the chemistry is changed, where there's a reduced resistance to corrosion. That's the location where much of the corrosion in steel pipelines will occur. And in fact, for steel pipelines, there's often a post-weld heat treatment at the joint to try to return the chemistry in the joint to more closely resemble the rest of the pipe. Polyethylene is, however, a single material. It's just polyethylene. It's a long chain molecule of carbon with hydrogen to each side, so two hydrogens to each carbon. Some regions of the polyethylene material are crystalline. They are indeed solid. Other regions of the long chain molecule we call amorphous. They're not really solid. The long chain molecule hasn't settled into a fixed location. And these are the regions when the pipe is under stress that the molecules can reline and they give rise to some of the very desirable properties of the polyethylene. So with polyethylene at the joint, the polyethylene extradate just softens. There is no change of state. Only about a ½ millimeter or so of the parent pipe material needs to soften to be fully mixed with the extradate material that we deposit in the joint area in order to form the bond. A Weholite pipe was originally designed to be a gravity sewer pipe. It wasn't anticipated that it would be used for continuous pressure applications. Gravity pipes usually experience pressures for only relatively short durations of time. And in normal gravity flow, the hydraulic grade line generally follows along at the top of the pipe, the obvert of the pipe. But with gravity flow, for sewers, there's typically periods where there is surcharge occurring and where you will get peak flows considerably higher than that for short duration. The standard to which the pipe is made, regular pipe, is made, ASTM F894, and it specifically identifies that the pipe made to that standard need only be designed as a gravity pipe. For elastic pipes, and most of these other materials that Grant spoke about are elastic materials, steel and concrete, the pressure rating for the material is fixed, is constant, regardless of the duration of the load. Essentially what that means is on a stress-strain curve, you're working in the linear portion of the stress-strain curve. Stress it, get a bit of a very small amount of lengthening, you remove the stress, and it returns to the original position. For hydropower applications and for irrigation applications, pressure hydraulic grade line is typically well above the obvert of the pipe, so it's under constant pressure. Figure 2 in this slide, or the figure that you see in the slide, illustrates the pressure balance within a solid wall pressure pipe. The vertical component of the pressure across the center line at ID in the upward direction is balanced by a downward pressure in the pipe wall for a given unit of length. And it's usually assumed to be uniform pressure within the pipe wall. In the steel industry, this relationship is known as Barlow's formula and is typically referred to as the ISO formula in the polyethylene industry. We have here a picture of finite element analysis of both a solid wall polyethylene pipe and profile wall Weholite. And for solid wall, the assumption of uniform pressure is actually only true for thin-walled polyethylene pipe. Polyethylene has really a lower stress, a lower allowable stress than materials like steel, so the wall thickness, even for solid wall pipe, is considerably thicker than it would be for a steel material. The allowable stresses for polyethylene would be about 1,000 psi. For steel, could be 30,000 psi or more. The FEA of a polyethylene DR11 pipe, picture on the left, indicates a stress distribution of about 520 psi at the OD and approximately 800 psi at the ID of the pipe. So there's about a 50% greater stress at the ID than there is at the OD of the pipe. The stresses, however, in the profile wall polyethylene pipe have a greater range of stresses. It's not just a distribution range of 50%. It's considerably higher than that. And the highest stresses are usually found, as you can see in the illustration, the picture on the right, in the middle of the waterway wall. The waterway wall here is the one at the bottom of the page, and the stress that's highest is in the middle, and basically that's bending moment occurring across the pipe wall between the ribs. There's also a region of high stress near the ribs or at the ribs that is highest really where the waterway wall meets the rib. So those are the two locations of interest. I think it's useful to have a little bit of an understanding about how polyethylene pressure pipe and polyethylene resins are raised. A qualification of PE pressure pipe is usually based on hydrostatic pressure testing of small diameter pipes at a series of reference temperatures so that the performance at 50 or 100 years can be determined by extrapolation. Clearly, we don't want to be testing pipe for 50 years or 100 years in order to know what its pressure rating is. And again, unlike steel, where the properties for long duration and short duration are the same regardless of low duration, it varies with plastic materials. On the right image on the slide is an elevated tank. Typically, all of this testing has to be done at controlled temperatures, and that's done by putting the samples of pipe in a tank. In this case, this is one of the elevated tanks where the water is at 80 degrees C. And in a tank like this, one can easily put 50 to 100 samples of small diameter tubing. So to determine the stress rating of PE solid pipes, they are pressurized at known wall stresses and left pressurized until failure occurs at a significant number of stress levels. So what you're seeing there on the little graph, each one of those dots is a failure point. Stress level on the vertical axis and on the horizontal axis, the duration at which the ductile failure occurred. So when polyethylene is tested at reference temperatures of 23 C or 20 C, and I state the two temperatures there because the reference temperature in the North American standards is 23 C, and in the ISO standard it's 20 C. The failure is usually ductile, and that means there's a ballooning of the pipe wall. And the data points, if you get a significant number of these, they can be extrapolated to times of 50 or 100 years as desired. And then factors of safety are applied to these extrapolated values. Typically, it's the inverse of really the factor of safety that we're using. We're using a design coefficient. In the ISO part of the world, they would typically use 80% of this extrapolated value, and we're more conservative in North America. We'd use about 63% of that. If one does sufficient testing at elevated temperatures, it would produce failures that are not ductile but that are brittle, slit-like failures. And testing at multiple elevated temperatures can be extrapolated to determine that we will not suffer slow crack growth failure with polyethylene resins. Please note that the plots that you're seeing here are log-log plots. Small decreases in stress give rise to very significant increases in the time to failure. So Uponor and its predecessor company have conducted a significant number of hydrostatic pressure tests on various wall geometries of Weholite. But given the size of the sample, we clearly cannot conduct as many tests as could be conducted for solid wall pipe, and we cannot rely only on hydrostatic pressure testing. Proprietary design modifications have been made to regular Weholite to produce low-pressure Weholite, which is the pipe that's used on these hydropressure applications. The design is internally qualified by a combination of assessment tools, including the hydrostatic pressure testing we talked about, some finite element analysis so that we can understand the stress level in the pipe, and finally, opportunities to monitor the performance of existing installations. Of grade as you're moving downstream, so there's an opportunity to have picked up a fair bit ahead by locating the power station at a downstream location. The Weholite was installed. It actually started some of the installation in 2007, but primarily completed in 2008. And you're seeing both ends of the Weholite portion of the project. Obviously, the start on the left and the completion on the right. You'll note there are bands on the pipe at each of the joints. Those are temporary. They're simply used to contain the PE extradate during the welding and are removed after that. There are only two access locations to the pipeline, and they're both near the limits of the polyethylene pipe. The design drawings for the access point are on the left. In the middle, you see us accessing through the manway, and the picture on the right is the last of the manhole just before we get to the steel portion. And there was no evidence of either ductile creep or formation of cracks at these manway access locations. The pipe that's shown in the sample here is not a sample of the Aberfeldie pipe. This is a standard regular Weholite portion. It was provided for this condition assessment to validate the accuracy of ultrasonic examination that BC Hydro was using as a means of checking for the remaining waterway wall thickness. They're trying to determine if there had been any wear on the pipe. So the UT equipment was checked against both the pipe and, against the reference block that you also see in the photo. And it was a very accurate tool for measurement of the waterway wall thickness. We checked that at a variety of locations throughout the 2,700 feet, but no wear was observed. And a separate third-party report is being prepared for BC Hydro with respect to the wear or lack of wear. This slide indicates two profiles along a straight edge, and you can see that there's no evidence of pipe wall deformation due to the continuous 20 psi internal pressure within the pipe. It's still a straight surface of the pipe, and there's no evidence of any ductile deformation in the middle of the profile wall, and no evidence of any crack formation near the ribs. And this is a picture, one taken in 2008, and the same picture taken again in 2017. And again, no visual evidence of material lost due to abrasion. And in point of fact, we've actually still have retained the sticker. So not only do we have good pipe, we've obviously selected some good sticker materials as well. Because the velocity in this pipe is 8 to 10 feet per second. It's at the first 55-degree elbow where there's considerable turbulence. So again, no evidence of wall deformation or any evidence of slow crack growth formation near the ribs. And a final slide here. I noted that the plots of time to failure are log-log plots. You see the same, which indicates that most of the deformation occurs early, and you're seeing that in this slide as well. On the bottom, we're indicating stress that's held at a constant level, and on the top portion here, most of the deformation occurs very early. So one would expect that inspecting this pipe at the 9-year point, that most of the deformation that would occur in a 50-year or 100-year period would already have occurred. And this really means that observations at this point are very good indicators of the long-term serviceability of the pipe. There's every reason to expect that the pipe will perform better than anticipated based on the proprietary wall design that we have implemented for this project. In point of fact, we're so excited about the excellence of the results that we may choose to move forward with a slightly different design criteria that allow us to offer a pressure pipe at higher pressures than we have traditionally been offering in the marketplace. And with that, I will hand this over to Daryl Sollenbach, the sales manager.
Thanks, Jerry, and good afternoon, everyone. I'm going to present to you case studies that we've done throughout the years, and there's about 10 of them, starting with Pacific Core. This was our first power project in the year 2000, so it's been in service for now 17 years. It's located in Big Fork, Montana, and the engineers on this were Black and Veatch. It's a 120-inch or 3,000 millimeter in diameter, operating at 8 psi. Tight, reliable joints was one of the criteria for selecting this material, as well as excellent flow characteristics. And long lengths reduce the installation cost. We can deliver our 10-foot diameter pipe in 42-foot lengths, and our smaller sizes up to 50 to 55-foot lengths. In this picture that you see here, water supply to the turbines was divided between a concrete-lined open channel and a buried wood stave pipeline. In this photo as well, the old wood stave line was to the left, and to the right is the concrete channel. The same alignment was selected for the replacement of the Weholite pipe, where the wood stave pipe used to exist. Since the buried pipe line was lower than the open channel, it operated under an average pressure of 8 psi. The lines function as an inverted siphon. The water from both the buried line and the open channel is being fed into the headworks, which are then feeding the 3 turbines to produce the 8 kilowatts of power. And notably, a small diameter perforated polyethylene drain line was placed along the 120-inch pipe to collect any leakage that may occur and to prevent the leakage from washing into the Swan River immediately adjacent to the site. And to this date, they have never seen an ounce of water drain through that PE pipe, so they have never had a leak in that line. So it served its purpose well. Our second case study is Rutherford Creek. It was built in 2003, 15 psi low pressure pipe, 2 sizes, starting at 120 inch from the intake down to 108 inch. Both are ring stiffness coefficient of 250. This is a run-of-river project, so there's no headworks at the very beginning, or dam, I should say. And this project's located 15 kilometers from Whistler, BC, has been generating about 50 megawatts of power. Contractor decided to rail the pipe from our plant in Saskatoon to Pemberton because they were concerned with construction delays along the highway, which is being upgraded for the 2010 Winter Olympics. So very forward thinking on this project. The next project we did was in 2008, Fire Creek, 84-inch. This is located near Pemberton, BC, and the only access point was through a logging road, which is about an hour and a half journey from the town of Pemberton. And this particular project is generating 23 megawatts of power. Next in line, and in the same area, same region as Fire Creek, and is generating 27 megawatts of power, is Douglas Creek, with a diameter of 96-inch RSC 250, again in 2008. And this is probably running at close to between 13 and 15 psi. If you remember the slide previously, the Fire Creek project was an 84-inch diameter pipe. This is 96-inch. They're both going to the same location. We were actually able to nest the 84-inch pipe inside the 96-inch pipe and saved half the cost of freight, which is substantial for these power projects because they're so out in areas that are hard to get to. And the third case study within this Fire Creek, Douglas Creek region is the Capella power project owned by Creek-Innergex. And it is the smallest of the 3 generating facilities at this location and is generating 18 megawatts of power. On this slide here, you'll see that after we pressure out at the 15 psi mark, that we'll flange into steel. And the reason for doing that, using 2 types of materials, that Weholite is so light, so easy to handle. You're on mountain slides. It's just a much easier pipe to deal with. It comes in longer lengths. You can drag this along the ground. You're not going to remove any protective coatings. And so that's the reason why you're using these hybrid type pipeline systems for these power projects. Next, we have the Aberfeldie project, which Jerry talked about in detail, located near Cranbrook, BC, and generating 25 megawatts of power, up from, when it was first built, 8 megawatts of power when it was first built. And this is and the Aberfeldie is 132 inch in diameter, and it was the first project to receive this 132 inch pipe. It was at the request of the consultants and the owners, BC Hydro, that we scale up from our previous large size of 120 to 132 inch, and we did so, and that's what was delivered to the site. Next, we have East Toba, owned by Alterra, again, another 120 inch diameter pipe, which was started and completed in 2010. You can see at the end of the pipeline there where we're going to be flanging into steel again. This power project is generating, this is one of our larger run-of-the-river projects, 123 megawatts of power. And the only access to this facility was either by boat, barge, and or float plane, so very remote. All the power generating facilities, all the camp, the pipe, everything related to this project had to be barged to the site. So it required considerable attention to logistics for this project, and it was built by Peter Kiewit. In the same cluster near East Toba is the Montrose, again owned by Alterra, 132 inch pipe on this. Basically, it's one length of pipe they used this was for the intake. Didn't continue on with any other pipe after that, but they saw considerable advantages to using this as an intake versus casting everything out of concrete. It's relatively close to East Toba with access only by barge or float plane again, and it's generating 73 megawatts of power. This was a very high elevation installation requiring our crews to actually take a course on avalanche safety, and you can see the quite severe winter conditions that are going on there in a coastal area, which is just lends itself to how high an elevation this is and how much snow they actually get up there. And then lastly, we have the last project that we installed in 2012. Which is the Kokish power project owned by Brookfield. 3 sizes there, ranging from 132 inch down to 108 inch. This project is located near Port McNeill on Vancouver Island and is now generating 45 megawatts of power. And the pipe was trucked to Vancouver and then ferried over. So freight for some of the larger pipe, the 132 inch, was as high as $9,300 a load. So another project requiring considerable logistics associated with it. And that is the synopsis of the case studies. Any questions?
Thank you, Daryl. So now that brings us to another poll question that brings us to the end of the webinar. So we'd like to ask you, would you, now having seen our webinar, would you consider using structural HDPE material for your Penstock projects? You can go ahead and give us your answers, and then we'll move on from there. Okay, so 95% of you say that you do intend on considering to use our HDPE Weholite material for your penstock, which is always that's the answer that we want. So thank you for attending, everybody. A pre-recorded version of this webinar will be available for later viewing and sharing with your audience. We will like to go through a few questions that we've got. So number one is, what's the life expectancy of structural HDPE penstock? Daryl, can you answer this one?
Certainly. We use a design life of 100 years for our pipe.
Okay. Second one here is, what's the largest diameter penstock that Uponor makes? I'll have Jerry answer this one.
If you're paying attention, of course, you've seen it numerous times. That's 132 inches. Really, there's a limitation there. We're currently tooled for that size, but the practical reality is that we're bumping up against logistical issues with shipping larger sizes. So it could be possible to go a tiny bit larger, but I think we are near the practical limit in terms of what logistically can be provided.
Okay, thanks again. If you do have any questions for our engineering team, there are emails on the screen of Mr. Jerry Groen and Mr. Daryl Salenbach. You can email them and they'll provide you an in-depth answer from the pertaining to penstocks and any other questions you have for Uponor Infra. Thank you again to Grant, Jerry, and Daryl, and to all of you attending. We will be sending out a PDH certificate to everyone that's attended with your name on it, and we'll also be uploading this on YouTube and sending it to you for later viewing. With that being said, I hope you have a great day, and thank you for attending.